Well, welcome back. And in this lecture today, we're going to talk about how carbon dioxide and other greenhouse gas variations are observed as changing in the atmosphere over the last few years. And in particular, looking at a range of different observational data for changes in carbon dioxide, and in particular, understanding what might have caused some of these changes in carbon dioxide variations. So we're going to look at something called the Keeling curve, which Dave Keeling was the first scientist to take long-term observations of carbon dioxide. We're going to look at carbon dioxide observations at a site in Australia over a long period, and then understanding some of these changes in carbon dioxide and oxygen. So the longest record of carbon dioxide from instrumental data anywhere in the world is from Mauna Loa in the Hawaiian Islands. And here's a picture of from a satellite data of the Mauna Loa volcano. Now, it's important to understand that if you want to identify or measure background concentrations of carbon dioxide, then you need to make sure that it's not affected by local pollution sources. So Mauna Loa is a very remote area. It's not really affected by any industrial activity nearby. We just have to be very careful that the possible emissions from the volcano aren't affecting the observations at Mauna Loa. And so what's done is to take the observations there when there are strong winds and no local effects from the volcano Mauna Loa itself. And then we can look at the long-term observations, and this graph shows the long-term variations in carbon dioxide way back from 1960. Here, if I reach back here, and you can see the progressive increase over time, increasing to concentrations to just about 400 parts per million. We're going to zoom in to that a little bit later. So there's a very strong increase over time in these carbon dioxide concentrations. And now let's zoom in to the last 3 years. And what we can see is a pronounced seasonal cycle with higher values of carbon dioxide in the winter and lower values in the summer. And that's really an indication of the global environmental system breathing in and breathing out. And what it really is an indication is that photosynthesis associated with plants takes up carbon dioxide in the spring and summer season, and then when the plants lose their leaves or die off in autumn and winter or fall and winter, those plants decay and release back carbon dioxide into the atmosphere. And so we can see here that at the end of the record in the last winter season in the Northern Hemisphere, there was particularly high concentrations just above 400 parts per million. At this stage, the annual average hasn't reached above 400 parts per million, but that's very likely to occur this year. We can also see what this range from one year to the next, this seasonal range, is about 6 parts per million. It's consistent with 2 to 3 years of growth in the annual from year to year. But we see that this seasonal variation between winter and summer is actually much stronger in Mauna Loa than it would be in air in the southern hemisphere. And we'll look at that in one of the later slides. So these observations, first of all, indicate what's happening from summer to winter, back to summer again. The whole Earth system and the vegetation system is taking up CO2 in spring and summer, so the carbon dioxide concentration falls and then releases that back out again as the plants die off. So yes, this is an indication of the important role of plants and vegetation all around the planet in taking up carbon dioxide, but it's also an indication with this steady rise that there's not enough uptake, that there's some long-term emissions. And the best evidence for the role of human activity is this long-term increase, and we'll look later on at some possible explanations for that increase. We can see this breathing of the planet in some of these satellite images of photosynthetic activity. The top image up here is a July or summertime image in the northern hemisphere, and the colours show the activity of vegetation. And here now in the northern hemisphere winter, there's much reduced photosynthetic activity, and now you can see that the strongest photosynthetic activity in the southern hemisphere summer is exactly there in the southern hemisphere. We also have a long-term monitoring site on the northwest part of Tasmania here in Cape Grim, and this is very good at measuring baseline concentrations of a whole range of different gases, because the air arriving at Cape Grim comes predominantly from the west, and there's no other land masses further to the west of Cape Grim until you actually go all the way around the planet, in fact further to the east to South America. So the Cape Grim observations also remove any air that's coming from the north and only take air that's coming from the west or the south. And this shows the observations of Cape Grim and the concentrations of carbon dioxide. This is the Cape Grim observations, and the superimposed on those is also shown observations of oxygen concentrations. And we can see that there's a long-term increase in the carbon dioxide, but at the same time, this long-term increase is around 1.6 and now accelerating to more than 2 parts per million per year. But at the same time, there's a decrease in oxygen concentrations. Now, the best explanation for that is associated with burning fossil fuels, because if you're burning something, in this case fossil fuels, you're taking up oxygen from the atmosphere, and the decline in the oxygen concentration is expected to be double the decline in carbon amounts, and that's exactly what we see. A decline in carbon dioxide concentrations that's double the rate of the increase in oxygen, and that matches exactly what we would expect from burning of fossil fuels. So what about now long-term variations in other greenhouse gases? And so this shows the changes in carbon dioxide that we've talked about before, but we can also look at long-term changes here of nitrous oxide over the last 40 years or so, from 1980 right up to the present, 2012. 2010, this is the carbon dioxide variations. This is the concentrations of methane from the same sorts of sites. And we see that methane concentrations grew rapidly, then they slowed down again, and recently they've started to grow again. Methane has a shorter lifetime in the atmosphere, and that means that it's removed more quickly, and so changes in the sources of methane affect more quickly the changes in concentration. And then finally over here are the changes in concentrations of the chlorofluorocarbon, or the ozone depleting chemicals that have been controlled by the Montreal Protocol, and we see that their concentrations in the atmosphere have in fact stabilized and started to fall. And these two chlorofluorocarbons now are falling, even though they've got very long lifetimes. The controls on their production and emissions by the Montreal Protocol means that their concentrations have started to fall, associated with destruction by UV radiation in the stratosphere or the upper atmosphere. So these show the variations of a range of different greenhouse gases, all of which have major human sources and all of which have long lifetimes in the atmosphere. And unfortunately, they're all growing. And we're going to look at whether these growth in the long-lived greenhouse gases due to human activity are actually having an impact on the climate in a later class. Now, one of the really interesting questions with the carbon dioxide variations here is what might be affecting, and we're going to look in the next lecture at the concentrations or the relative proportion of carbon-12 and carbon-13, the isotopic variations of carbon-12 and carbon-13 in the carbon dioxide variations up here. And that's very important in trying to understand the sources of these concentrations of carbon dioxide in the atmosphere. But we'll talk more about that when we look at long-term variations in carbon-12 and carbon-13. But notice that this is a reversed scale, and the carbon-13 amount is falling in the atmosphere. This is a scale which has been reversed, and this indicates a fall in the carbon-13, and that's associated again with carbon that's been photosynthetically processed being added into the atmosphere compared with carbon that might be the normal concentration. So we're getting a change in the amount of carbon-13, and again that's due to photosynthesis. And fossil fuels are associated with old plant material buried underground between 50 and 100 million years ago. We can also look at long-term variations in the climate from a range of other archaeological and geological evidence. And one of the really interesting aspects is that we can identify long-term changes in sea level over the last 10,000 years or 100,000 years associated with changes in the coastline. Where the University of Melbourne is at the head of Port Phillip Bay, just here to the north of the bay here. And the bay coastline is shown by this darker colour. But actually, if the bay, Port Phillip Bay, is relatively shallow, and there is myths or stories in the dream time of the local indigenous population, the Wurundjeri peoples, that talk about a river extending all the way through this region and all the way out, and that the original coastline was much further away. And in fact, the bay, the waters in the bay are quite shallow. And this is consistent with sea level being about 100 metres lower, more than 10,000 years ago when the Ice Age was at its peak. The most recent Ice Age finished about 15,000 years ago, started to decline about 20,000 years ago, and this current relatively stable period in the climate started about 10,000 years ago. We call that the Holocene. And these myths or stories in the dream time from the local indigenous people, the Wurundjeri tribe, help us to understand that yes, this geological evidence really was affecting the local indigenous tribe here in the southern part of Australia. So we can use a range of different sources of evidence. We can measure the concentrations of carbon dioxide and look at those variations, and the observations that we see show that there have been marked increases in carbon dioxide, as well as year-to-year or season-to-season variations with uptake of carbon dioxide in the northern hemisphere in spring and summer, and return of that carbon dioxide back into the atmosphere in the northern hemisphere autumn and winter seasons. There's been a steady increase in carbon dioxide over the last 100 years, and where we have good data, we can see that over the last 30 years or so, there's been a match, a very good match of the decline in oxygen together at the same time as the increase in carbon dioxide. And this is entirely consistent with the changes in fossil fuel use. Burning fossil fuels is using up oxygen, and that's associated with the increase in carbon dioxide. Now, we don't have to worry about the decrease in oxygen. It's a very, very small fractional change. But yes, it precisely matches the increase in carbon dioxide.